Hi, and welcome to our presentation about trends in spectroscopy at the EPIC Photonics Plus Virtual Conference 2021. My name is Martin Labus, and I'm Sales Engineer for Optical Test and Measurement and Spectroscopy at Laser 2000 Germany. Our headquarters is located in the Munich area, one of the hotspots of the German photonics industry. Laser 2000 has more than 35 years of experience in nearly all fields of photonics and local offices in France, the Iberian Peninsula, and Scandinavia. Our passionate salespeople provide our customers not only with our wide product portfolio, but also with our know-how and experience in many applications. One of the strongest growing spectroscopic methods within the past few years is definitely Raman spectroscopy. This is due to the fact that laser sources that are powerful and narrow line width has become more and more cost-effective, and also modular spectrometer solutions with cooled and high sensitive detector have become more and more affordable. Raman spectroscopy is easy to integrate because the only thing you need is some kind of optical access to your sample. May it be by a probe, by a microscope, or even by using simple optics like lenses or objective lenses. And Raman spectroscopy provides simple spectra compared to other spectroscopic methods, where you do not necessarily need some big amount of chemometrics to evaluate the data. But the Raman effect is typically weak, so you obtain weak signals that can easily be obscured by some kind of luminescence background. But there are ways to overcome this. So you can move your excitation when coming from 532 nanometers in the visible range or 785 in the very near infrared range. You can go up to longer wavelength, like 1064 nanometers, for example. So this has the advantage that nearly all of the luminescence background vanish, but you will have to search for a higher power laser source as the Raman scattering efficiency goes down with longer wavelengths. Or you can go the other way around and move to the deep UV region, maybe like 250 nanometers. This has the big advantage that you get in the same way when you go down to shorter wavelengths, a much higher Raman scattering efficiency, and you somehow keep the information from the luminescence background, but it separates from the Raman spectrum itself, as the Raman spectrum is dependent only on the excitation wavelength, and the Raman shifts are directly related to the excitation wavelength. They will follow the excitation wavelength to the deep UV in this case, but the fluorescence background in that special case will stay always in the same region as it has been before, as the excitation of a fluorophore is somehow fixed in wavelength. And so you get the higher scattering intensity, you get the information from the Raman spectra, and you can also evaluate the luminescence spectra. Another interesting technique for Raman spectroscopy is definitely Raman concatenation, because you can use a smaller modular spectrometer with a more or less restricted wavelength range. When I say restricted, it is I mean, when using a modular spectrometer, you normally can cover a range of, let's say, 200 wave numbers to about 2000 wave numbers. But in Raman spectroscopy, this is only half the truth, as this is only the so-called fingerprint region in Raman spectroscopy. So if you want to see the stretch region, you can follow two paths to achieve this. You can, on one hand, use a bigger detector array. So it's just broader and takes the entire spectrum, let's say from 200 to 4000 wave numbers, or you can take the entire spectrum in 2 shots at this point. So what do I mean with 2 shots? So you have a design wavelength for your spectrometer, let's say 785 nanometers. So then you excite with your 785 nanometer laser and get the fingerprint region as stated before, so 200 to approximately 2000 wave numbers. So if you now want to cover the second range, the stretch range with the upper wave numbers, you can just shift the wavelength to a bit shorter, so exactly the amount that your detector covers, and then take another shot. As I said before, the Raman spectrum is directly related to the excitation wavelength. The fingerprint region will go out of the detector's range, but now the fingerprint region will come in. And in this way, you can take a Raman spectrum, an entire Raman spectrum, 0 to nearly 4000 wave numbers in 2 shots. Another point, what's in nearly every application in spectroscopy is interesting are portable and handheld solutions. In the best case, with direct online database access to provide easy quantification and qualification and identification of your samples. In general spectroscopic application, especially talking about absorption, reflection, transmission purposes and applications, also there is more demand for industrial use. But one counterpoint in the industry is USB is not the preferred type of connection as it is with most modular spectrometers. So there are a variety of connection types necessary to satisfy industrial customers' needs. So these connection types can be analog, digital, Ethernet, I2C, or even wireless. Everything for most industrial customers, nearly everything is better than USB. Another point here also is a rising demand for handheld or portable analyzers, especially for field research, or let's say also for quality control purposes, where you just point your handheld at your products and then get directly some kind of control if the specifications are fulfilled. And of course, as halogen lighting is more and more displaced by LEDs and solid-state lightings, especially for the sake of energy saving or energy efficiency. So it's nearly everywhere necessary to provide proper lighting measurement, as when you change your lighting type, you normally change the color temperature, or LED and solid-state lighting don't have the same spectrum as sunlight or incandescent light. And therefore, for appropriate digital reproduction, or especially also for printing purposes or for use of displays, it's very, very important to ensure high quality color reproduction and brightness and so on. And for this sake, colorimetry, radiometry, and photometry are used to, even when you change your type of lighting, you always get the same results. As we're all working, or many people are working from home right now and have to deal with some kind of laptop monitor and maybe some extra monitors, you will all, or many people will have faced the problem that you have you have an Excel sheet on the one monitor and an Excel sheet on the other monitor, and the background white color differs just because of the type of monitor you use. So, and therefore, especially for those people who work professionally with that kind of monitors, like graphic designers and so on, it's very, very important to have a natural and consistent, color reproduction in that case. And especially as the displays and the monitors are always getting bigger and bigger, you have to take numerous spot measurements of one display to ensure that all regions are the same. And therefore, it's good to know that there are solutions to provide 2D measurements, especially of large areas, to perform a 100% quality control. So thanks for watching this video. For any questions, just visit our local website and find your personal contact. Contact us via email or via LinkedIn. Thanks. Goodbye.